Okay, so here's another problem about boxes and the normal force. This one's a little bit trickier for two reasons. One is we have to worry about um, a force acting in two different directions. So this force is at an angle, so we're going to have to worry about x and y components. And the other thing that's different is this is a dynamics problem, so not everything is at rest, things are actually accelerating. Okay, so here we have a 5 kilogram box sitting on a frictionless table, and someone has tied a rope to it and pulls on it with a force of 20 newtons in a direction 30 degrees above the horizontal. So we're told that we should start by drawing a free body diagram, so let's do that. So we'll draw a free body diagram for the box, and this box has three forces acting on it. It has gravity pushing down as always. It has the normal force, which is always perpendicular to that surface, so perpendicular to the table. And now there's also this 20 Newton force of somebody pulling on it. There. So that's our free body diagram. And because we have forces in two different directions, I'm going to define the x and y axis to be the horizontal and vertical axes as usual. So that's part A. So from here we can move on to part B, where we want to figure out what's the magnitude of the normal force in this case. So, So going back to the free body diagram, we can look and try to figure out what direction, if any, this box is accelerating in. So because it's sitting on a table, we think it's probably not moving down into the table. It's probably not levitating above the table. It may be accelerating in the horizontal direction that someone's pushing it. So it could be accelerating to the right like this. So there could be, in fact, it looks like there is a net force in the x direction, but it should not be accelerating in the y direction. So we can say that the sum of the forces in the y direction has to equal m ay, but ay is equal to 0. And so the sum of the y components of the forces must equal 0. And to identify those forces, we have the normal force, plus we have that 20 Newton force, or at least the component of it that's in the y direction, and we have mg in the minus y direction. That has to equal 0. So let's just go back up to the free body diagram a bit. This 20 Newton force is going off at an angle, and you guys remember how to do this. It's a vector, and so we can decompose it into its x and y components. So that's a 30-degree angle, and that means that the x component is 20 newtons cosine 30 degrees, and the y component is the 20 newtons times sine of 30 degrees. Okay, so back down here, we can rearrange this equation and say that the normal force is mg, so that's 5 kilograms times 9.8 meters per second squared, minus 20 newtons times sine of 30 degrees. And putting this all together, that is 49 newtons minus 10 newtons, or 39 newtons. And that makes sense because the person who's pulling on it is pulling up a little bit, and so that reduces the amount of force that the table needs to apply to the box to keep it upright. Okay, so part C asks, what's the net force on this mass? So, like we said before, this mass may be accelerating. In fact, it is probably accelerating in the x direction, but it's not accelerating in the y direction. So if there is a net force, it must be acting in the x direction. So the sum of the forces in the x direction, actually the only force that has any component in the x direction is this 20 Newton force. And the x component of it is 20 newtons cosine of 30 degrees. And so that is 17.3 newtons. So we could say, see, it's asking for the net force. We can say the net force is 17.3 newtons I hat. Okay. So for part D, now it asks what's the acceleration, and we've been doing this step by step, so it's been sort of leading us further along this path. So if we want to know the acceleration, we just need to use Newton's second law. The sum of the forces is equal to the mass times the acceleration. And we just found the sum of the forces, or the net force, and so we can say the acceleration is then the net force over m, or 17.3 newtons I hat over 5 kilograms, or 3.5 meters per second squared I hat. Okay, so this whole thing is accelerating in the x direction at 3.5 meters per second. Okay, so part E asks kind of a funny question. Going back and changing things around, what would change if the normal force on the rope, instead of being 20 newtons, became 200 newtons? So 200 newtons is kind of a lot. Okay, so let's redo the calculation of the normal force now when the force on the rope is 200 newtons. So to calculate the normal force, we just took the net force in the y direction, which was the normal force, plus the force of the rope, 200 newtons, the y component, so sine of 30 degrees, minus mg, and that said that it had to equal to 0. And so the normal force was mg minus 200 newtons, sine of 30 degrees, which was 49 newtons minus 200 newtons times 0.5, which in this case looks like it's going to be negative 51 newtons. So what does it mean that we tried to calculate the normal force and we got something negative instead of something positive? So if you want to pause here for a second and think about what that might mean before I move on, now would be the time to pause and think. Okay, so what does it mean that the normal force is negative? It doesn't really make sense. We think of a normal force as something that pushes, right? In this case, the normal force is pushing up, keeping the block on the table instead of falling down to the floor. If the normal force was negative, that would imply that the normal force was like pulling the box down to make sure that it didn't like levitate up off the table. And that doesn't really make sense. You'd need like Velcro or something to have a negative normal force. So what this means really is that the 200 Newton force that the person is pulling with now is so strong that in reality the 5 kilogram box would no longer remain on the table. It would get sort of pulled up off of the table. So what would happen here would be, there's my table, and now, oh, here's my box. The person is pulling on it. Soon it's gonna just come fly right up off the table. And so this minus 51 newtons is not really physical in this situation. That's like if you needed Velcro to keep the block stuck to the table, which is what we're assuming. So, but a more realistic situation is that now probably the sum of the forces in the y direction is no longer actually equal to 0. Probably you'd actually just have some acceleration in the y direction as the person pulls up with such a strong force. Okay, so the negative 51 newtons is not really a physical answer.